Hello, my name is Wilfred van Wiel. I'm at the University of Twente, Mesa Plus Institute for Nanotechnology, and at the Brain Center for Brain-Inspired Nanosystems. Today I will talk about material learning. Let me also take the opportunity to thank the organizers to invite me for this keynote presentation. Before starting, let me acknowledge my co-workers. As you can see, there is many people involved. This has everything to do with the multidisciplinary character of our work. So we have people from physics, we have people from electrical engineering, chemistry, machine learning, and applied mathematics. Well, I talked about our center, the Center for Brain-Inspired Nanosystems. So where does this inspiration from the brain come from? So let's have a look at a comparison between man-made information processing systems and the human brain. Our chips, our processors are very good at logical operations and doing computations with high precision and with high speed. On the other hand, our brain has evolved to be very good at interpreting the outside world. A typical CPU at the moment can do about 10 to the 11th operations per second. And although it's hard to make a direct comparison, a brain can do approximately 10 to the 15th operations per second. This is done by about 100 billion neurons and 100 to 1,000 trillion of synapses. And that's also where the amazing computational power comes from, because many things happening in parallel, as opposed to a man-made chip where there is a central processor and basically computation is sequential. Maybe the most amazing thing of all is energy consumption, and that also forms basically the main source of our inspiration. Whereas a typical processor uses about 100 watt for this 10 to the 11th operation per second, our brain typically only consumes on the order of 10 to 20 watt. So it's logical that we try to somehow imitate the idea of the natural brain. And an abstract way of doing that is in the form of a so-called artificial neural network. You see many nodes in this network. These nodes represent the artificial neurons, and they are interconnected via these artificial synapses. So in this network, all of these nodes are connected from one layer to the next. In this model, when the sum of the weighted inputs passes the threshold, the nonlinear transfer function of the neurons go from 0 to 1. The weight and threshold values are being trained in the process called machine learning. And when this artificial neural network has many hidden layers, as in this case, so apart from the input layer and the output layer, one speaks of deep learning. Deep in the sense that there are many layers between input and output, and therefore also many artificial neurons to be trained. The problem, however, with these artificial neural networks, in particular the deep neural networks, is that digital computing hardware is very wasteful for using for this machine learning tasks. And what we see is a transition to application-specific hardware, and in particular, brain-inspired or neuromorphic hardware. And this is what you can see here in these editorials a couple of years ago, that we need a hardware revolution, basically a kind of renaissance to allow for carrying out these algorithms efficiently. So this neuromorphic hardware or brain-inspired hardware is also identified by the European Commission as one of the 100 radical innovation breakthroughs for the future, next to, for example, quantum computation. An example of a neuromorphic chip was introduced by IBM in 2014. It has 4,096 cores, and each of them having 256 programmable simulated neurons, so reaching about a little bit over 1 million neurons. And every neuron has 256 programmable synapses that convey the signals between them. So hence the total number of programmable synapses is just over 268 million. It uses 5.4 billion conventional transistors, and by this multi-core approach it circumvents somewhat the von Neumann bottleneck. IBM claims a energy consumption of about 70 milliwatt. The next goal of IBM is to go to 4 billion neurons and 1 trillion synapses, but that would already consume 4 kilowatts. So if you compare that to the 100 billion neurons and 100 trillion synapses of the brain, you see this goes way beyond the energy consumption of the brain, which is just 20 watt, as I said before. Another example is this one, Loihi by Intel. It has also a multi-core approach, about 130,000 neurons and 130 million synapses, and it uses 2 billion transistors. What we can see here is that actually the footprint is very large, so in total something like 16 square millimeter, which is an issue if you would like to insert this technology in mobile devices or Internet of Things or computing in the edge. If you compare this with the brain of a honeybee, it has many more neurons, about 1 billion synapses, and only occupying a volume of 1 cubic millimeter. So what we need for lowering this energy consumption and having a small footprint is really radically new solutions. This is why we started a couple of years ago in 2018 our Center for Brain-Inspired Nanosystems. It combines core expertise in nanoscience and nanotechnology with expertise from computer science, artificial intelligence, applied mathematics, and neuroscience to lay the scientific foundations for a new generation of powerful, energy-efficient computing hardware. So we use all kinds of adaptive materials. We use the concept of material learning, and in particular evolution in material, which I will explain in a moment. We also try to interface with CMOS and even biological systems, and there is even an eye for societal implications and philosophical aspects of our work. Here are two examples of computation. One is the standard digital computing building block, the NAND gate, which is a universal building block for digital computing. And on the other hand, here again, a simple artificial neural network. And what is crucial to both paradigms is nonlinearity. So for writing out the algebraic expression for NAND gate, you would get this expression where it's the nonlinearity apparent, but also these nonlinear transfer functions of the artificial neurons are very nonlinear in essence. So now if we would like to come up with a concept for computation which is very economic in using materials, we should find a source of non-linearity. And that's the idea. We don't want to use conventional building blocks, so still silicon-based CMOS, but instead of that we try to exploit the physics at the lowest aggregation level for computation. So you could say we want to do immaterial computing. And therefore, as I explain here, we need this nonlinearity. Well, when we started this endeavor a couple of years ago, we thought of using single electron transistors as a source of nonlinear switching. So what you can see here on the right is a tiny gold nanoparticle. It's 20 nanometer in diameter, and by molecular glue, it's connected to these gold nanorods. So on this scanning electron microscope image, you basically see a single electron transistor based on a single gold nanoparticle. And by these external electrodes, we can apply a voltage and measure the current through such a system. Well, this is a very well understood system and can be described by the physics of Coulomb blockade. So here you see a transport diagram. On the horizontal axis, there is the gate voltage, which is the backgate below this particle. And on the vertical axis, you see the source drain voltage. Then a characteristic pattern occurs where there is regions of suppression of the current, referred to as Coulomb blockade. If you open up the bias a little bit, then you get into a regime which is referred to as single electron tunneling, where only one electron tunnels at a time on the particle and tunnels off again. And then if you open the bias window further, you can go into double and triple and so on electron tunneling regimes. As you notice, to see this single charging effects, you have to go to rather low temperature. So in this experiment, we even went to just a couple of millikelvins, which is of course not very practical for applications. But the point I want to make here is that although these single devices can be still very well understood and described by relative simple equations, if you go to a much more complicated structure, so a network of many of these particles, it becomes completely hopeless to predict what the behavior will be. And that was the idea of trying to exploit the physics of this very complex system in order to see whether we could somehow train it into a functional device. And that's described here in this paper of a couple of years ago now. Let me explain a bit further what we have in mind. We exploit the so-called concept of material learning. So now instead of machine learning that people use for training their software models, we now are going to train to learn a material directly into a functional device. In particular, I would like to explain the concept of artificial evolution or evolution in material. So here in evolution in material, two domains exist, a physical and a computer domain. And in the physical domain, we apply a certain physical input to a material system, and we read out the physical output. The material can be tuned and manipulated. Its properties can be changed by some knobs called physical configuration or the control. So in our case, these could be in the electrical domain. Once we have caused an input-output relation, we bring this to the computer domain and then apply we compare the actual physical output with a desired output. And we assign a certain fitness value to that. Depending on that fitness, we can change the physical configuration, and we do that in a quasi-genetic way. So the number of controls here can be seen as genes, and we apply the tricks of Darwinian evolution. So we have mutations, we have crossbreeding and selection and so on, to get to a new physical configuration of the material. After that, we again measure the input-output relationship, map it back to the computer domain, determine the fitness, and so on. So we get an iterative process in order to optimize basically a black box system that is formed by our material system. And after a certain number of iterations or generations, if you like, we hope to arrive at the desired functionality. Well, let me become a little bit more concrete. So here we have a schematic of our nanoparticle device again. It consists of a wafer with on top 8 metallic electrodes. There's an open region in the middle where the nanoparticles are collected. We use 2 of these electrodes as voltage inputs. We have these voltage pulse trains, and we measure the current from one of the other electrodes. And the rest of the electrodes and also the substrate is used as gates. So the controls to change the physical configuration of this nanoelectronic system. So for example, as you can see here on the right, we could try and realize the logic AND gate. So here you see the truth table of the AND gate. It should only provide a high input, a logical 1, if both inputs are high. So if we look here in the physical domain, only when both voltage inputs are high, then the current should be high. Otherwise, it should be a low current, ideally 0 current. So a priori, of course, our device won't behave like that, but by applying this concept of evolution in material, we try to arrive at a configuration of our system that behaves exactly like that. So here we see an image, an AFM image on the left of our actual device. So you see that it is very disordered, but we don't care about it. We don't need to make any a priori structuring besides the electrodes, basically, because we use this concept of material learning to arrive at functionality. These are the inputs as a function of time. You see that in this experiment everything goes rather slowly, because the point is not to arrive at very high speeds, but just show the proof of principle. And here are the results, again at pretty low temperature. So on the top you can see inverter gates. So we have 1 input, 1 output, and these are exactly the inverses of the input signals, both for signal P and Q. And the lower 6 windows show here 2 input, 1 output gates. And interestingly, within about 50 to 100 generations of our genetic algorithm, we can arrive at all basic Boolean logic gates, including the very tough exclusive OR exclusive NOR gates. I will come back to these specific gates in a moment. So this is very promising that in principle we see here that without too much effort and basically effortless in terms of design, we can make functional devices. The only problem is, of course, well, not the only, but one of the main problems is that we have to do this at very low temperatures to be able to exploit this nonlinear physics of single electron tunneling. So what we did more recently is that we moved to a completely different materials platform. So from this gold nanoparticle network, we moved to silicon and more specifically to a system of boron dopants embedded in a silicon host. The basic geometry remains the same. We still have an active region of typically 300 nanometer in diameter and also 8 to 12 electrodes along its perimeter. With this system, I'll tell you more about some different functionalities beyond also Boolean logic. A little bit more on the device. So here you see again a top view, the 8 electrodes and the central region. In order to arrive at a nonlinear system, we basically need to use now the physics of variable range hopping. This happens at relatively low dopant concentrations. So when we dope the central region, we have to etch down to arrive at a typical doping concentration of about 10 to the 17th per cubic centimeter, in which at lower temperature this variable range hopping regime occurs, as you can see here on the left. So basically up to around 150 Kelvin, you see that the IVs are very nonlinear, and we can use that nonlinearity for realizing our functionality. A little bit more on the physics of variable range hopping. Here we map out the resistance versus inverse temperature, and this is the general expression for the conduction. So we see that at relatively high temperature, so from about 250 K and up, we basically are in the band conduction regime. That is typically the regime in which conventional devices such as transistors are being used. However, if we go to lower temperature, and the data is plotted a slightly different way, but for now it doesn't really matter. But we see that for a region about 100 Kelvin, between 70 K and 160 K, we are in the so-called variable range hopping regime. This comes with these nonlinear IVs. From the exponent here in the expression for variable range hopping, we can derive that we basically are in a two-dimensional limit. So transport basically takes place in a plane close to the surface of our device. And the nice thing is that this happens basically up to around 100 to 150 Kelvin, so we can operate our devices at much higher temperature as compared to the ones that we used before with the gold nanoparticles that had to be operated at sub-Kelvin temperatures. Well, first of all, basically as a benchmark test, we repeated more or less the experiments that we also had done on the gold nanoparticle networks, but this time at liquid nitrogen temperature of 77 Kelvin. So the idea is again the same. We have these time-dependent voltage inputs that we apply to two inputs to the device, and we measure the output current. In black, there is the ideal output for the respective gate, and in red, you see the actual output current after the artificial evolution algorithm has been run for typically up to 50 generations. So also here you see that we can realize all Boolean logic at 77K in this case. But the nice thing is that if we push our device a little bit to the limits, we can even see the exclusive OR and exclusive NOR gates at room temperature. Although you see that the signal to noise ratio is not so high as at lower temperature here. In principle, we think this can be ascribed to non-idealities of our present device structure. So we are quite hopeful that we can operate our devices in the next generations at or very close to room temperature. Well, I already emphasized a few times the difficulty of the exclusive OR gate, and this has to do with the following. Basically, realization of the exclusive OR gate can be seen also as the solution of a nonlinear classification problem. So if you look at this left graph here, basically what you have here is a graphical representation of the truth table of an exclusive OR gate, where red corresponds to a high output and blue to a low output. So you see only if one of the inputs here along the x-axis is high, only one, then also the output is high. And when both inputs are low or when both inputs are high, you will have a low output. So this is the exclusive OR problem. When you now turn it into a classification problem, you could say, well, what barrier, what decision boundary do you need to draw to separate these two classes, the blue boxes and the red dots? And you will see that it's impossible to draw just a straight line to separate the two. You have to basically draw a nonlinear decision boundary. So that makes this classification problem a linearly inseparable problem. Now, what we could do is apply a trick and basically transfer this two-dimensional problem to a higher dimension. So in this case, that would be the third dimension. And via a nonlinear transformation, we can map these data points here now in the 3D space. And after this transformation, as you can see, there is now a linear plane possible to draw, which nicely separates both classes. Now, if we, for example, take the distance to this plane as a new variable, we can basically very nicely depict now both classes and very easily separate them. So we move from 2 dimensions into an intermediate excursion to a higher dimension, the third dimension, and then go back to 1D where we can easily classify. This is generalizable to much higher dimensions, and that is what we are going to use our device for. So we have our nonlinear device. Here what you see in green is kind of the potential landscape that charge carriers see when they travel from input to output. And this potential landscape is tunable by the control voltages. So if we map now the inputs to low inputs, for example, like here, of a low and a high input, we'll see that the trajectories of the charges are different. So in the case of 2 low inputs, we will have low output, whereas for this case, low-high, we will have high output. So what you see here is that you basically get an intrinsic mapping to this higher dimensional space, higher dimensional parameter space formed by our device. So we don't need to do this non-linear transformation by explicit calculation, but we get basically quasi-instantaneously an answer given by our device if we train it into the correct potential landscape. This is a very useful property, because otherwise you have to do a couple of sequential operations. That's what you would have to do in digital computing. So let's see how we can apply this nonlinear transformation property to another problem. And for that, we use this benchmark problem of the handwritten digit database provided by MNIST. This is a database of about 60,000 handwritten digits, and you see an example of this here now, with which you can train your normally artificial neural network. And then there is another set of 10,000 handwritten digits to validate your neural network. What we do is we use that approach, but we build in our hardware, our physical device, to carry out the non-linear transformation part of this classification problem. How do we do this? Well, what we do is we want to focus on critical features inside these handwritten digits, somehow similar to this canonical experiment done by Wiel and Wiel, where they showed that specific areas in the cat's brain are very sensitive to certain features, so very critically dependent on the orientation of these bars. And so only for a certain angle, certain neurons will start to fire. So there are what we call feature extractors in this biological brain, but we can also define artificial feature extractors. And that's exactly what we are going to do. So what we define is, since our device only has a limited amount of inputs, we start looking for the moment only at 2 by 2 pixel patterns and black and white pixels. So there are 16 possible configurations of these pixels. And for every configuration, every feature, we define by our control voltages a device setting that reacts specifically with a high output current to a certain input. So in this example, you see that this device setting, this feature extractor, reacts with the largest current for this specific input, for this specific feature. So we make one configuration, so in total 16 for every possible configuration. So not all of them are very well separated, but that is not really important as long as we can identify from the amplitude of the current with what feature we are dealing as input, we are able to make a transformation. So for a given input, 2 by 2 pixel input, we feed them to all these 16 feature extractors, and judging from the largest output current, we can basically extract what kind of feature we have as an input. Of course, the handwritten digits are much larger than 2 by 2 pixels, so we have to do a convolutional approach. So we scan this 27 by 27 pixel image, black and white image, with this window of 2 by 2. So we scan along every time when we offer this feature, it will be seen by these 16 different feature extractors, and in this way we can finally train the outputs, these weights, in a linear layer here, so that we finally can map by a pseudo-inverse learning step to which of the 10 possible answers the input image belongs. So this is done in a conventional computer, this linear classifier, and the crucial thing is here that mapping here to this high dimensional space, this comparison with the 16 feature extractor, is done quasi-instantaneously by our device. Now, if we look at the overall accuracy of this procedure, so it's a kind of hybrid procedure, partly done still in conventional computer and partly done by our hardware, we see that we get an accuracy of total accuracy of 96%. So in 96% of the cases we have a correct mapping, and that's quite remarkable if you look at here at the possible digits that you can have. Some of them are really very hard to identify. This 96% you could compare to the accuracy that you get if you only have a linear classifier. So that would be without our device incorporated. So there is really a significant improvement as compared to this 88%. If you now look at state-of-the-art deep neural networks, then you see that we are not completely there yet. So for completely software-based deep neural nets, even 99% is reached. In this paper, we projected that under optimum circumstances, so optimized setups, optimized for speed and bandwidth, we should be able to do 100 tera operations per watt per second. And that is actually getting very close to the operation speed of the brain that I mentioned to you at the beginning of this talk. Well, another example of what we can do with our system, where we not only have binary inputs, so like in the logic problem we have only a 0 or 1, or in the feature extractor problem we have only black and white, so basically again only 0 and 1. In this problem we call it the ring classifier. We have two classes of data, so in the middle you see here a class in green, which is in the middle of a circle, and then this outer class, there's many data points around with a circular decision boundary. So what we have to solve here is basically a closed circular decision boundary where the input can have non-binary values. So basically there's analog input. So what we want is that our device gives a very well separable current depending on whether the data point belongs here to this green class or the black class. What you already can see here in this color plot, our device can do that. It gives the highest current here in the middle. So for this class, we call this class 1, we have high current, and for class 0 on the outer rim we have lower currents. So it's easily based on the output current, just on one variable. It's possible to separate these two data sets. And that's not trivial. If you want to use an artificial neural network for that, you would need at least 3 hidden neurons. And our device does that in one go and at an area of only a few hundred nanometers. The last thing that I would like to discuss with you is the most recent work where we have used an alternative for artificial evolution to train our devices. Artificial evolution is very nice because you can directly operate on the physical system. You can think of it as a black box, and then by this artificial evolution you can find optima, or local optima at least. What we did here in this work was that we first made out of our physical device basically a conventional deep neural network model. So we start with measuring the input-output data of the device, and we make, based on that input-output data, a sufficiently deep and wide neural network, where the numbers of inputs and outputs match those of the device. The deep neural network is then trained with the measured training data and tested with unseen test data. Now, we use that model, once it's ready, to find the desired functionality through gradient descent on the control parameters. So once we have our digital copy basically of our device ready, we keep all the weights and thresholds constant, but we leave the control parameters open. So we use often used algorithm called gradient descent to find the values of the control voltages that we need to get a desired input-output relationship. So for example, an AND gate or an XOR gate or whatsoever. The interesting thing is now that we can basically do offline, so not directly on our physical device, but in the model, in a computer, we can use standard machine learning algorithms to find a solution for, let's say, an AND gate. Now, once we have found these values for the control parameters, we can go back to the physical device and apply these values that we have found in the deep neural network model and apply them to the physical device. And very nicely, we can see that this works neatly and that we can indeed measure in real life the desired functionality. few more words on how to do the data acquisition for such a device, because you can imagine that you have to collect a lot of input-output data before you have a sufficiently good representing model. So what we do is we have this kind of parallel mechanism where we apply periodic signals to the voltage electrodes, and we do that so that periodicities form irrational ratios. So the frequency have irrational ratios. And here you see an example just for two parameters in the two-dimensional space. So by doing this, we can basically scan very nicely and densely the parameter space without having to make instance jumps, which could lead to transients and capacitive effects. Because we use this irrational ratios, we can avoid that certain input combinations are being replicated. So this is a very nice way of scanning the parameter space, and also an efficient way. Well, also with this system we tried to solve this ring classifier, and we succeeded in that. But now the solutions are found not by artificial evolution, but about 100 times faster using our digital copy, our deep neural network, in combination with gradient descent. And this problem is now more difficult. We have only a gap size of 400 millivolt. You can see here the output currents. High corresponds to class 1, that's in the middle, class 0 in the middle, and low current corresponds with class 1 in the outer ring. Another example here is feature mapping, where we now feature or we map 16 different inputs features to different current outputs. So having only one output, we can map these very nicely in different current levels, with a separation larger than noise level, so that we can discern what feature is being offered. All right, let me conclude with that what we have been trying in the last couple of years is basically make a transition from machine learning to material learning, where we try to realize hardware suitable for implementing artificial neural networks. But I would like to emphasize that you not necessarily have to think of making artificial neural networks. This concept is much more general paradigm of computing, of material-based computing. We use the intrinsic and mostly the nonlinear physical properties to compute. And the big advantage is that you can exploit all the physical properties at hand. You don't need to first limit yourselves to building blocks like transistors and capacitors. Basically, you can use all physics at hand to realize your functionality. That's a big advantage. The other advantage is that you are not so prone to defects. You don't need to have a perfect device layout, but you can start with disordered systems and then use material learning to realize the functionality. That's at the same time also the downside. For every individual device, you have to go through this learning phase, because no device is the same. What we have shown is that we can realize functionality at a very small footprint and with a projected high energy efficiency. And the last thing that I have showed you was efficient training using a surrogate model consisting of a deep neural network. This is an alternative, as an intermediate step, an alternative for this artificial evolution. With that, I would like to thank you for your attention, and I'm available for questions. Thank you very much.